works. So hi, I'm Paul Norman from Ford Motor Company. My co-authors on this work are Ori Soamimo, our summer intern, and then Nils Tomey. Like Burkhard mentioned, we're going to look at an initialization sensitivity study. So looking at how does the initialization of the solution of DrivAer case 2a on the committee mesh influence the final results. This is specific to a transient solve. A typical process is doing the meshing, initializing with some method that you hope approximates the final solution, and then starting the transient solve. So we'll look at swapping out different methods, including RANs mapped from a coarse mesh, high time step DDS, and then potential flow. And in each case, we'll use small perturbations to improve the statistics. The key questions we'll look to answer are, number one, are the solutions from the initialization, are they more different than what we'd expect from the time series noise? Because any change we make will trigger time series noise. And number two, which initialization method has the least burn-in or stabilization time, and which is the most computationally efficient? Our simulation details are here. It's the same as the previous workshop, AutoCFD4 with a time step of 2 times 10 to the -4, and then run time for 12 seconds, averaging for 10. So I know this is quite long, but this was just to collect robust statistics. Next, looking at the different initialization methods. First, it's for RANs, we actually start from potential flow and then run the RAN solver. This is a picture of a Y slice of the RAN solution. So this is the steady state time average solution. So quite different from what a snapshot of the transient solution would look like. For different perturbations, we run, I would consider the baseline 1500 iterations, then we run small perturbations on that by solving for one more RANS iteration, so 1501 or 1502. And that would show up as really small changes in the contour plot here. And additionally, we run one for a shorter amount of time when RANS is not yet quite converged or at steady state, 750 iterations, and then one for 6000. And the runtime of this method is 1 hour for 1500 iterations. Next, we look at initializing from coarse RANs. So that's same as RANs, but I'm running on a coarse mesh, 30 million cells. If I toggle back and forth, you can see the effect of coarsening. And maybe this isn't the best use of 30 million cells. I think if you tried to give me 30 million cells and get the best result, we probably could have done better because the drag coefficient ended up being quite a lot larger. But this is just an example of a coarse mesh. And worth noting that this method is a lot faster than RANs. It takes 20 minutes and also 10 minutes for the meshing, then 10 minutes for the RAN solve. So in addition to being faster than the RANs initialization, you have the potential to run it in parallel with your typical meshing process to totally mask the initialization time. It would just be the mapping. Next, we look at high time step initialization. So this is a snapshot of the flow field. So fluctuations of the wake, quite different from the RANs. We ran for a high time step of 2 times 10 to the -3, 10 times the normal time step with a first order upwind convection scheme because I didn't want to have any numerical stability issues. I ran in increments of 1 second, and this is going to be, a greater impact on the initialization because unlike the RANs results, it's not going to be small perturbations. It's going to be quite different snapshots. And this takes about 1 hour for 500 iterations. Finally, we just tried initializing from potential flow. This runs really fast, 30 seconds, and multiple signals are produced by adding a small perturbation upstream to one of the cells. So just after potential flow is done running, just editing one of the cells by a very small amount. So a note on perturbations, this is just kind of an explicit way to trigger time series noise. So I've given an example here of a simulation that I restarted, one just to restart and another with a small perturbation upstream. So you can see the wakes are the same initially, but they do diverge quite quickly over time. And you can see this in the time series here or the correlation coefficient of the 2 time series. So you can't produce completely statistically identical signals, but it's the best we can do for initializations. Next, we'll look at the results. We look at everything as a scatter plot of CD and CL. These are the RANs results, and then I'm labeling each point by the number of RANs iterations. So my takeaways from this are no definitive trend with the number of iterations in the initialization. It's not like these numbers are all sorted. A larger spread in CL than CD, which I think is typical. We've seen that in the other results. And then also some apparent correlation between CD and CL, which we'll talk about later. Next, adding the coarse-mesh results, I would say no definitive trend with the number of iterations again, and also not very different from RANs in terms of the scatter. Next, adding the high time step results. Again, no real trend with the number of iterations, but generally we do see a lower CL and perhaps CD than the other result. And then interestingly, we see an outlier here for this one run initialized from 2 seconds of high time step DDES. And that's not to say the simulation was crashing or the residuals were different. The time series just ended up at a different average. And interesting to note that this outlier failed the mean calc stationarity test with a confidence interval of 97. So it's a great tool to identify things like that, because it's one thing to see an outlier in a plot like this, but another thing to have a tool that could tell you if a point is potentially an outlier based on the time series. And finally, putting the potential flow results on here, I would say not really different from the other ones, except for an outlier for one of the perturbations. Again, nothing really different about this simulation, other than the time series looks different. And again, this outlier fails the stationarity test, this time with a higher confidence interval. So next we'll talk about whether we could explain the scatter due to purely time series noise or whether it's actually due to the changes in initialization. So we're going to go into a little bit more depth with the method. I just wanted to give a background on the mean calc method. This is how you estimate the uncertainty in the mean of a time series. Basically, what you do is you batch the signal up into batches of, say, 0.5 seconds in this example here. You take the average of each batch, and then you take the standard deviation of the batch means. And then you can increase the batch length and extrapolate with time. And as Charlie and the folks at Upstream has pointed out in this great paper, generally this trend follows a t to the negative 1/2 trend with time. So this is it's a great thing to know, and I think it was commented on the previous talk, is that it lets you know how the uncertainty in your time series error is going to decrease with time, this t to the negative 1/2 scaling. So for example, I ran for 10 seconds, but to half the uncertainty, I would have to run for 40 seconds. So it kind of lets you know where the point of diminishing returns is. So we'll take this method one step further. So in addition to looking at the variance in CD from time series error and CL, we'll also look at the covariance and illustrate why we want to do this. Well, besides the scatter plot where we saw that correlation, if I take the batch means of one of my time series signals, each one of these points is a average over 50 steps, and I increase the batch length, I can clearly see there's a correlation between CD and CL. After all, the force is just a vector, and the big fluctuations are happening on surfaces that are not just up and down. So what we do is, rather than using error bars, we use a confidence ellipse, like I think discussed in this great matplotlib article. So rather than having an up and down error bar, you draw an ellipse around it, which accounts for the covariance in the process. And then to figure out what the variance and the covariance are, we again use a similar process to mean calc, where you do the batch means and extrapolate with time. And I took the same t to the negative 1/2 trend to extrapolate with covariance. Now, if I had to do this all over again, what I did here is I used a conservative style fit, where you basically put a line on the topmost point. And I think it's fine to be conservative about the variances, but I realized after the fact that I shouldn't have done this for the covariance, because it actually biases the result. So my confidence ellipse is actually clocked counterclockwise from where it should be slightly. So if anyone does this method again, maybe fit the principal ellipse axis instead. Applying this confidence ellipse to the scatter plot on the previous slide, this is a 95% confidence ellipse for the RANS initialized results. So I've taken the average variance from the RANS signals, assuming that those are all the same in covariance, and then taken the ellipse center as the center of all the points. So the first thing to note is the RANS results all lie within the confidence ellipse. So you would say probably what we're seeing there is nothing more than time series noise. Whereas interestingly, all the other points, or all the other initialization methods, have one or more outliers. So you would suspect that something is going on there that is due to purely the initialization. And that's not to say if we ran for even longer that this would eventually wash out. This is just what we have observed over the first 10 seconds. And then more qualitatively, I mean, but just from a CFD process, both the RANs and the coarse RANs results produce a pretty tight clustering, so a very consistent process. So I do like these results. I had a slide on where the error is on the surface, or where the differences between the results are, and I think we saw this in one of the previous presentations, but it's kind of the usual suspects: the base, the backlight, and some places on the wheel arches. And you can take it one step further and apply the mean calc algorithm to say the time series of the surface pressure to determine where this noise is typically going to be. So this is in contrast to looking at the standard deviation on the surface of the pressure, which I'm toggling back and forth between here. So basically it's the standard deviation of the pressure weighted by places where there's low frequency noise. Additionally, you can do a cumulative integral of the random error to see where the big contributors are going to be. Finally, looking at the burn-in and stabilization time, there's a lot of different ways to look at this. Kind of qualitatively, just to eyeball the plots, what I did is for each initialization method, I averaged across all 5 time series and then took a 0.5 second windowed average. And you can see the burn-in pretty clearly here for potential flow. It starts pretty far away from the solution. There's this huge overshoot, and it takes like 2 seconds to reach a stabilized state. And you see this to some extent for the high time step initialization too, and to a lesser extent for the RANS results. But to get more in detail, rather than just eyeballing the plots, we can use mean calc, the stabilization time estimator, which is a lot more sensitive. And applying this to the results, we found that the RANS initialization had the lowest average stabilization time, as well as the lowest maximum stabilization time. So providing generally a lower burn-in time than all the other results. And this would dwarf the difference in the computational cost of the results. So the conclusions of the study are we studied the sensitivity of swapping out the RANS initialization with other methods, coarse RANS, high time step, and potential flow. For this case in our code, the RANS initialization definitely had the lowest stabilization time, and then coarse RANS and RANS had the tightest grouping. That's not to say coarse RANs and high time step initializations are wrong or anything. They're still, I think they're used in practice in many places and they work fine. But in this case, I would say further work is needed on their implementation. So maybe for coarse RANs, I could have done the mesh refinements better and gotten the drag coefficient closer to the final value. And for the high time step initialization, I think that first order upwind scheme that I used really smeared out the results and meant that the burn-in time was longer because the drag coefficient had a longer way to go. So I recognize the results are not general to everyone's setups, but I just wanted to show an example of how you could study swapping out initialization methods. What we did, multiple simulations per initialization method to trigger time series noise with perturbations, which gives more data and better statistics. Carefully considering whether your differences are arising from time series noise or actually what you're studying, in this case, initialization. And then using a great tool like mean calc or something else to analyze the time series error, stabilization, and any non-stationarity. And like Burkhart mentioned in the beginning, as part of the noise TFG, we conducted quite a number of different studies evaluating the noise. We've put a summary here, and you can ask Nils, who's there in person, for further details. We looked at a number of things, including initialization, changing the surface mesh, changing the decomposition, the CPU type, the volume mesh, and noise from geometry changes, as well as the estimated impact from these. Although the devil's very much in the details and about how you do the simulations. So that's it for me. Any questions in the room?